speakers from CMCC Italy, Professor Antonio Navarra, who is the head of CMCC Foundation Italy. And we have Dr. Ronan McAdam from CMCC Italy. So let us first hear the talk from Professor Antonio Navarra. A short bio about the speaker. Antonio Navarra is a professor at the University of Bologna. He graduated in physics at the University of Bologna and then moved to the Princeton University to get a PhD at GFDL. He is also the president of CMCC Foundation, a multidisciplinary research center whose mission is to investigate and model the human climate system. He has an extensive experience in climate numerical experiments and on numerical methods as a tool of scientific investigation and discovery. He has also held appointments as affiliate scientist at NCAR and in the advisory board of APCC South Korea. He has been on the board of ECMWF Council, Joint Programming Initiative Climate, and the board of the UN Adaptation Fund, and much more. But for the time constraint, I am just inviting Professor Navarra to provide this talk. Thank you.
Thank you very much. Oh, yes. Thank you very much for the invitation and giving this talk. I hope that I will not like this, right? Yeah, I will not boring you. You know, while I was preparing this talk, I was wondering, what can I say anything new to this kind of audience? That's really tough to do in a way. So I decided to try to make a journey with you, just to make, just to make a little bit of reflection, taking a moment on some of the fundamental issues in our field, especially in this particular juncture, where in a way we're experimenting a paradigm shift in how we proceed and we work. So let me remind you what we do. We actually study the climate system. This is the climate system. I don't need to be very specific, except to note that everything is kept together by water. And water is really what is making the climate so. Condensation process and evaporation process, every time that a droplet change state, that contributes to the defining what is the climate state, right? And our job is actually to try to take, in a way, accounting all these transformations so that we can finally end up what is the status of the climate. And, you know, you probably have told many people to your students, many times to your students, how complex this is. And we all know it's difficult. If you've been trying to calibrate a GCM, you know it's very complicated. And it's very complicated, and that poses a problem because usually science is trying to simplify, is trying to reduce. So, for instance, we could easily take out the water and say, okay, let's study the climate without the water. We can do that. It's marginally more simpler, but it's not our planet. So we have an irreducible problem in our hands. So how do we do? Well, even geographical limitations are a problem because we have a set of teleconnections that are linking all the planet together. So climate is globalized much before everything else. So we cannot even take that shortcuts. And so that is a little bit of an issue because, again, science works by reduction. So we would like to reduce the problem to something. Actually, we would like to reduce the problem to such an extent that we arrive at a crucial juncture. That was usually is a moment in which experiments decides which hypothesis is right. That's a crucial experiment. This is a photograph of the Michelson and Morley experiment. If you know what it is, that's wonderful. If you don't, that doesn't matter, because what matters to me is that that's a table. These experiments change the way we see the world. The interesting thing for me is that this experiment was made by two guys on a table in what looks like a basement. So they changed the world in a basement. Now, that's a crucial experiment. Now, I would like to make a crucial experiment. Are Himalayas really important for the monsoon? Let's take out the Himalayas and see what happens to the monsoon. Is the Mediterranean really drying up 2 meters every year? Let's close Gibraltar and see if the Mediterranean dries up. That would be a great experiment to do. But they don't give us the money. They don't give us the permission to do those experiments. So how do we do? How can we make a scientific approach to climate, to a science where we cannot make experiments? So it's a little bit of a problem that we solved by creating virtual representation of our planet we call models. So once we have this numerical representation, then we can make the experiments. So in our models, we can take out the Himalayas, we can close Gibraltar, and probably some of you have done those experiments. So we can do those things. So, but how we made it here? Well, the lucky part was that we had the equations, and so that was important. But we arrived here through a complex process because we went through a process that first was mathematizing the natural system. So we were capable of actually representing the natural system that we were wanted to describe through a set of equations. That's a mathematization problem. So basically, nature is transformed into a mathematical expression. Okay, that's not guaranteed. If you talk with economists, they claim they can do the same thing, but in reality, they don't know because they don't really know what, or let's put it this way, they don't agree on what are the mathematical expressions that are fundamental. So that's not guaranteed that you can take a natural system and express it as a set of mathematical relations. But then we did something more. We did modeling. Modeling is exploiting mathematization by creating a hierarchy of progressively more complicated representation of reality that are trying to represent complexity. So they're trying to resolve the conundrum of having this complex system that has to be approached via reductionist paradigm by creating a hierarchy of models. Each one of them are more complex than the other. It is guided by theoretical intuition. That's what we do. And if you stop one moment and think about it, that's what you do every day. You're trying to create increasing complexity and making sense of what we do. And as I said, this was not always like this. We are a very young science. Until the start of the 20th century, basically there were three main development lines. There was a very strong empirical activity consisting of recording observations and try to infer something from the observation. It was very descriptive. That was climatology at the time. So climatology was a descriptive science, was not a predictive science. There were theoretical activity, try to explain the phenomena on the basis of general physical principles, using the laws of physics as they were being developed. This is the line that eventually established dynamic meteorology as a scientific enterprise. And then, of course, there was a very strong practical activity that was trying to do weather forecasting. And the prediction was basically based on experiment and experience and almost no theory. It was practitioners try to make forecasts. So that was the situation basically at the beginning of the 20th century. Oops, I think. Sorry, I'll go back to that. But then something happens, two things. The first one, I would say the opposite order. Wilhelm Bjerknes was a professor of geophysics, and in his inaugural lecture when he was made professor in Leipzig in 1913, he wrote a wonderful paper in which basically laid down very clearly the principle by which mathematics and could be used to make the science of atmospheric sciences and weather forecasting really, in a way, scientific. because he was claiming that if we had enough observation, then the initial state of the atmosphere could be represented, and then the distribution of 7 variables could be obtained, and then from this chart as a starting point, you could actually predict everything else. So this was a mathematization issue. It was basically saying, if I have the initial condition, I could actually use this equation to predict. But he didn't know how to do that because he was basically relying on graphical methods. They were, let's say, not very efficient. So the next step you need was the idea of Lewis Richardson, where in a book that is now 100-year-old, basically laid down the way of realizing Bjerknes' ideas. The idea is that you can take those equations and construct approximations numerically, basically trading the complexity of the equation with a very large number of elementary operations. And if you can do the calculation fast enough, you can actually realize Bjerknes' idea. So Bjerknes had the foundational mathematical intuition that if I know the initial condition, I can predict the future. But Richardson really gave legs to this idea by actually telling them how to do that. And what we have done in the past 100 years, we have realized this program. That's what we have done. We have realized that program to the fullest extent. Still, this early effort had some problems, and the problems was that Richardson had a good intuition, but the equations were much tougher than he was actually thinking. There were a number of issues that were made the naive application of this method a little tricky. That's what we call today the issue of stability and sound waves and this little thing. And to be clear, theoretically, so these 2 steps were not enough. The theory of atmospheric motion was behind. So it took about 20 years until the early 50s, where basically the theory was advanced enough to realize that the equation had to be changed a bit in order to make suitable for being solved by Richardson method. And so Charney's project, that was really inspired by John Feuernomen at Princeton, was capable to show that you can actually use Richardson method to solve the equation of the atmosphere and therefore produce the first numerical forecast. Now, that's an important date, okay? This is an important step because what happened here was to show that numerical approximation were a suitable, effective, and efficient method to address the issue of atmospheric forecast and simulation, we'd say today, and therefore was the way to apply Bjerknes' theoretical ideas of using mathematics in this context. In some sense, you might say that this is the birth of weather, atmospheric sciences, and climatology as a science. And the science meaning what? Microphone. It's not working. Yes. Now it's working. Now it's not working. Now it's working. Okay. All right. So this is I would say this is the moment in which we became a science capable of doing predictions, of doing experiment and testing hypotheses. We could not test hypotheses before. So this is a very important moment. And since then, has been a very roller coaster journey, right? I mean, development has been enormous. I mean, we started developing numerical forecasts, time marching differential equation. Initial condition is dominant, very important. Enormous effort to find methods to get accurate initial condition, extensive observation networks, enormous work to create system in which data can be made accurate, estimates can be accurate, using a data simulation to actually include constraints into constructing the initial condition. And all of this was because we were aiming at skill in this forecast. And we thought the skill was a direct function of the accuracy of an initial condition. Well, of course, also model quality, okay? But the idea is that the initial condition is the thing that you want to make sure is right, because even with a good model, if your initial condition is bad, you have no hope. On the other hand, if you have an accurate initial condition, a very bad model, you're also in bad shape. But because of data simulation, these two things go together. And so if you have a good model, you also have good initial conditions. So the thing created a feedback loop that basically reinforce each other. So enormous development, but it was not guaranteed. While this was happening in the 50s, it was not obvious that dynamical forecast was the way to make forecasts. Norbert Wiener at MIT had different ideas. Norbert Wiener thought that there was no need to use dynamical equation, but statistics could do the job. So there was a discussion between the John Neumann group and then Jules Charney when he went to MIT, and then Norbert Wiener. There was at the same MIT, and one was predicating the use of dynamical model, and the other one was saying, no, statistics is enough. And so they decided to set up a project to find out who was right. And the lead of this project was Ed Lorenz. And Ed Lorenz presented these results in 1960 at the Tokyo Symposium. That if you look this photograph, the photograph, or maybe I have that, I'll show you in a moment, where discussed this issue. And it was a very important symposium. A number of the basic concepts that we are taking for granted today were actually initiated here. One, this is an example, Eliassen, for instance, predicated that it would be in principle by using weather forecasting technique, by making them over a long period, therefore making statistics, and this maybe would be the way of making climate. So this is the first time that people start thinking that one could go from weather to climate with the same tools. So the same tools that were used to make weather forecasts could actually be used to investigate climate if you integrate long enough, that were good enough to make statistics with it. And it's interesting because it's saying that at 1960, since mankind is all the time changing the properties of the planet, there are really artificially produced changes of climate. And maybe one is thinking of in producing such changes deliberately. It is vitally important that we should be able to predict the effects before we try to change the properties of the planet. Well, that's not what we did, actually. We're making a very large experiment in which we're changing the planet, and we are not really sure what happens. But anyway, so that was interesting. So there was the level of discussion. And when Lorenz presented the paper on the results of this project, the results was that statistics was incapable of representing the weather beyond day one. And the argument was that the atmosphere is too nonlinear for the essential linear technique, statistical technique that were available in the 50s to be able to predict the weather beyond day one. So that was the end. Then dynamical methods were king because people abandoned statistical methods because it was clear that the system was too nonlinear, and the sort of autocorrelation AR system that were the dominant statistical method in the 50s could not compete with the dynamical models. So everybody's happy, and then trying to make these forecasts. But once again, Lorenz came in the game. And in this workshop here, this was 1972, in Washington, is presented this work about the sensitivity to initial condition. He himself then realized that the equations are complicated enough that small differences in the initial condition may actually result in very large differences down the integration time. Now we know that basically you can do anything you want to the model and you generate different states, right? You can change parameters, you can change boundary condition. It's not just sensitivity to initial condition, it's sensitivity to everything, right? So this means that deterministic ideas, the idea of making a forecast, all the effort, I get initial condition, very accurate, the best I can, and then I produce the best forecast in the world, is not going to work, or at least it's going to be challenged severely. And so what shall we do? You see, we were at a point in which our science was supported by very strong narratives. So in the 50s, the narrative was weather forecast. So if you ask anybody, if you have to tell your parents, when they ask you, what do? You would say, well, I'm working on weather forecast. They would understand. And then in the 60s, the narrative changed to let's put the entire planet in the model, general circulation models. And that's what people did at GFTL and Joe Spangorisky and the others. Then the 70s, the dream was, why stop at 3 days? You have to do extended range forecast, medium range, 10 days. Can we make 10 days? That's a dream. Then ECMWF is set up just to do exactly that. And then in the 80s, again, when people start realizing the El Nino was not such an unrealistic thing, well, maybe we can do seasonal forecast. We have bigger computer. We can use couple models. We can put the ocean in there. And so now we can extend our forecast to months. Benefits for everybody. And then we start to connect with the economic and social issues. And then in the 90s, climate change rose. So this is even bigger than all this, right? Then climate change is not even meteorological problem, it's a geopolitical problem. As a scientific problem, it is finished. I mean, we know what is causing it, but basically we know everything. So science-wise, it's done. So we have a little problem. What do we do now? What is the narrative now? What is our major driving idea in which we can push and tell our students, get into this enterprise because we try to go to the moon. I mean, we're trying to do something. So we have a problem. And I think this is something that collectively as a community, we have to think about a little bit more. So in this effort of trying something, people were trying everything, right? So the Hasselmann in 1976 tried to make a particularly synthetic representation of sensitivity to initial condition, sensitivity to everything, by basically representing the climate system as a dynamical part plus a stochastic part. So this was a recognition that there is something that we can't really control. Because you see, fundamentally, the mathematical description that we have sort of created for the atmosphere is not stochastic, it's deterministic. But this is a sort of, surrender to the fact that the sensitivity is so extreme that it may be more convenient to assume that the system is stochastic and therefore allow for a stochastic component in an otherwise deterministic part. So the idea is that we know this. This is the physics. This is our pride and joy. This is where we know the processes. And then there is other thing that we don't really know what it is. But nevertheless, if we put these things together, maybe we can get a better understanding or more power in controlling and predicting the weather, even the climate. So we were trying to do something. And people develop all sorts of things. For instance, the question was, is this function here really nonlinear? Maybe we can get away with linear stuff again. This is statistics getting into that. Again, all these people developing the linear inverse models, where basically the operator was identified with a linear evolution. And in some places, it works surprisingly well. You try to do sea surface temperature forecast in the tropical Pacific with this, it works very well. So there are places on Earth where basically the evolution of the system can be represented like this. Now, if you try to use this to make a seasonal forecast for temperature over Europe, it doesn't work. because even if the SST representation can be represented this way, the way the atmosphere takes that SST and transform it into anomalies in the mid-latitude is way nonlinear. So this all gave rise to a field, an entire field of research, that's predictability studies that you know very well, that basically is starting from the discovery to sensitivity. And then they developed of course, the next question is, what's the predictability limit? You know, how much we can push this? The historical famous work by Ed Lorenz had placed this limit about 2-3 weeks. So the deterministic prediction, therefore, is somewhat different. So how we try to do this? See, well, we developed the idea that we need to make many forecasts. If there is sensitivity, then we have to make many. We did ensembles. So basically, we accepted the fact that there is inevitable uncertainty. The forecast is not a single forecast, it's a bundle of them, it's an ensemble. And the intrinsic variability is actually due to this sensitivity. So we changed the problem. We basically said, well, we are not trying to do the forecast of tomorrow's weather, but I'm trying to determine what the probability of events in the future is. So we sort of changed the target. We are not talking anymore about a definite instant in the future, but we are really talking about the evolution of the probability distribution. Now, that's a major conceptual change that we did not do. We kept thinking in terms of deterministic forecasts. And the ensemble for us was simply a bunch of trying many things together, but we never really thought that we were shifting the problem from the instantaneous state of the atmosphere to the probability distribution of something. And I can understand that, because how many variables we have in, say, in a model? A few millions. So if we think in terms of probability distribution, that the probability distribution is depending on a million variable, you know, probability distribution, one variable is a Gaussian. Everybody's happy with that. If you have two variables, it's a Gaussian in two variables, still okay. Three variables is already getting difficult. You can't really make a plot of a Gaussian in three variables. Now, a Gaussian in 15,000 variables, it's something that makes no sense. So we have an issue with probability in highly dimensional space. What does that mean? We can't figure that out. And in fact, what we're doing, we're changing representation. We're moving from a trajectory representation of time to a bundle representation, of the forecast, right? So we're changing the way in which we're looking at things. This is our forecast, this will be our target, and now we're making a bunch of them and try basically to sample around a specific line. So is there any way to do this? Basically, we're shifting from a local representation. So basically, I'm interested only in this trajectory to a global representation. I'm interested in the property around this trajectory. It's a very strong conceptual shift. We haven't really done. Theory has not followed this shift, even if in practice, that's what we've been doing every time we're doing an ensemble. What was happening? Well, on a completely different line, something else was happening. In the 30s, Bertrand Koopman wrote two papers together with John von Neumann, where he basically, there was mathematical papers, so nobody read them. But in a nutshell, what these papers are saying is that given any dynamical system as a dual is equivalent to a linear operator. Unfortunately, the linear operator has infinite dimension. That was the reason these papers were ignored. Because if you take, say, the nonlinear pendulum that you can actually solve, that is equivalent to the infinite dimensional linear operator. I mean, nobody wants to do that. But John von Neumann was interested because he was hoping to get the equivalent of quantum mechanics for classical mechanics. Actually, you cannot do that, but that's a different story, okay? Anyway, so these results were very interesting. So basically saying that for every, let's see, for any system of this form, there is a linear operator that is a totally equivalent. So you can either study this system or you can study the linear operator. It's exactly the same. But as I said, this was ignored because it was simply too complicated. And it's even more interesting because that operator showed that is linked to another operator that was studied even before. That is the one that is forwarding in time. So it's evolving the probability distribution corresponding to the state space of that dynamical system. So the duality was double. You have a dynamical system, and you have a probability distribution, if you want, the density of trajectory for that dynamical system. And then you have two linear operators on the other side. One is actually acting on the state itself. The other one is acting on the probability distribution of the trajectories. These things were developed in theoretical mathematics, and everybody was ignoring them happily while we were doing our forecast. By the way, this is known Perron-Frobenius operator. It's a very well-known operator in dynamical system theory. So as I said, all this were ignored until about 10 years ago, where people start to realize that you could use some technique developed in deep learning to actually compute estimates of this operator from data. Not only that, but these techniques were so powerful that you could apply that also to highly dimensional data. And so a number of papers came out allowing you to do that. And they would also treat the nonlinearity in the system by basically including nonlinearity in the estimation. So they're very powerful technique you can apply to really complex system. And then if you wonder why you can do that, is that possible that any nonlinear system is equivalent to a linear operator? Well, think in these terms. Assume we have this simple equation here. I can actually make all this position. In a way, this is what happens when you try to close turbulence. When you try to close turbulence, you have an infinite sequence of equations that basically you can linearize them. They are linear. So you can expand. The price of getting linearity is that the number of variables increases enormously. And so if you allow that number to go to infinite, you have a linear operator. So this is a very profound result. It's really making a very close connection between nonlinearity, dimensional spaces. This is telling you, and there are now a very active line of investigation try to use this concept to explain why deep learning works. Deep learning is doing something like that. It's taking data and then expanding them in highly dimensional space where you can do operation easily, and then you go back. So there is a connection, and there are evidence that some of the neural, the deep learning networks are actually realizing approximation to the coupon operator from the mathematical point of view. Okay, that's already said this. So this is just the duality that I was. And okay, so what's the advantage of having a coupon a linear operator? Oh, you can apply the entire machinery of the composition of linear operator, right? You can do the spectrum, the eigenfunctions, and of course, life being complicated, sometimes the eigenfunctions are nice and discrete. Sometimes you have a continuous spectrum. So that's, I can tell you right away that chaotic system will have only continuous spectrum. Multi-periodic system will have only discrete spectrum. So you can classify all the system that you have, irrespective if they're linear or nonlinear. So you can apply the entire machinery. And now there is an extensive literature that is giving you mathematical guarantees that the results you get are robust, converge, blah, 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 and everything happy. You know, these things that make mathematicians happy. The estimation can be done from data, and you create this sort of matrices, and basically using extension of dynamical mode decomposition. That's one way. There are many ways of doing this. The using dynamical mode decomposition is one, or extended dynamical mode decomposition. And you create this approximation. And basically, you include the nonlinearities in the system. So what you get? Well, what you get predictors. Once you make this kind of decomposition, then you can construct linear predictors from the spectral decomposition of the operators. This was an example where we basically used it on the El Niño 3 time series. So what we get was the predictor for the probability distribution. And this shows the evolution of the probability distribution from an initial condition in time. So you can actually predict the probability. Now, this was a simple case because one dimension, but you could actually do it even in higher dimension because you can compute all the moments of the probability distribution without having to actually even knowing the probability, the exact form of the probability distribution itself. So you can apply this to the SST. And this one is an example. This is one of the modes that you get from such an analysis. This is a mode at 3.4 years. And so this will basically give you the kind of evolution. And you get all the modes and the corresponding eigenvalues. You can try to reconstruct the Niño 3+4 indices by using different composition of the modes that you get from the SST. And here you can analyze basically this. You show that the modes that are stationary are actually the major responsible for the variability of the Niño 3+4 variability. And then I can construct predictors, linear predictors of the SST itself. This is an example in which this is nonlinear Koopman kernel. This is basically LIM. And this was a case in which we were showing that with the nonlinearity, we could actually increase predictabilities in several cases up to 8 months. This is not just the index itself, it's the entire SST distribution over the tropical Pacific. So what this means? Well, it means that we are changing the way in which we're doing scientific investigation. We used to have models and theory. Now we have data, and they're connected with the new statistics. The reason statistics is now playing a role again is because we have these powerful nonlinear methods that have entered the game. So the deep learning network, the Koopman decomposition, all these methods are making statistics competitive again because they're nonlinear. So they're basically overcoming the limitation that Ed Lorenz found in the 60s when they basically, in a way, is Norbert Wiener vindication that he was right to some extent. But now we have a sort of triad because now we have models, we have theory, we have data, but data are not simply, how can I say, the support of models. They're actually an active part of this triad because you can actually extract information on processes, on evolution, and so on from the data itself. So that's the strongly nonlinear methods that we have developed allow us to do today. And that's how things are going to probably phase out. What we've been doing in the past was that we had data, then we have some first principle mathematical theory, then we do a lot of calculation, and then we do the diagnostic and analysis. That's how we've been working. But in the future, things will work probably different. We will have a multitude of data sources. Then we will have layers of data that will be both coming directly from observation, but also from models. And then all this will be ingested into some deep learning pipeline that will include not only the natural data, but also maybe socioeconomic data. This will produce impact analysis in a much more direct way that we're doing today. So the way we're going to work is going to be different. So this kind of workflow is going to be substituted with some realization of this. And the situation now is such that we are not really sure what form this new setup will take, but they will be certainly different from the standard way of working that we have done in the past 30 years. And this is the last example. This is GenCast. This is an example of one of the deep learning models that are basically showing that they are as good or even better than the state-of-the-art weather forecasting models. And in a way, this is another important moment, right? This is a moment like Charney's 1950. This is a moment where it's been shown that this new class of approaches, these new models, in a way, this is like the appearance of numerical solution in the 50s, is actually capable of doing complicated things. So it's a crucial moment. And if you're a student today, you're very lucky. You're in a very special moment today, because in front of you, things are opening up in a way that probably were not so open 10 years ago. So this field is going to get very crowded. And if the top of Mount Everest is crowded like this, so imagine deep learning, and because the resources are going to be limited, the amount of resources that's required to do interesting thing in deep learning are less than the crystallites. If you think about it, before this, if you want to do anything interesting in climate or weather, you needed a model and a computer. A model is encoding maybe 2,000 years of man work into it, and the computer costs a lot of money. Now, if you think about doing the same with the AI ML system, well, all these numbers are smaller. They're not insignificant, but they're smaller. So this means that we'll see a lot more actor in the game that we used to see. So it's going to be very crowded. And when the field is crowded, you see, if you take the same route that everybody's taking, it's going to take a long time. So either you go this way, so you need to be very, very smart, or you have to take an helicopter. That's the other possibility. But what we're trying to do what we always are done, and we certainly want to go boldly where nobody has ever gone before. That's certainly when we're going to go at CMCC and together with you. Thank you very much.
Thank you, Professor Antonio, for the inspiring talk from the evolution of NWP to the new emerging deep learning. So now we'll open the floor for the questions.
Sure.
Please.
Thank you very much. Very interesting talk. I have a simple question. So by doing machine learning, what do you think that we can bypass completely the what we have the initial error problem?
Initial?
In the numerical model, we have a big problem with the initial error.
Okay.
Error in initial condition, right? So by doing this machine learning, can we completely bypass this problem?
The machine learning models will have to rely on initial condition exactly like the dynamical model. However, there are realization of this model that will take as input not just one initial condition, but a sequence. So they will take many instances in the past to predict one instant in the future. That's changed the game, and it's not clear how this will impact the sensitivity to initial condition.
Okay, so maybe we may have a different kind of butterfly effect in machine learning.
We may or may not. That's to be investigated.
Oh.
And I think that's one of the active research area right now. Because you see, the way in which we have designed the problem until now was basically rely on the initial condition at one time. So the idea is totally from math, right? We're saying if you knew the initial condition at one time, that determines the evolution of the system forever. This system allows to take into account also previous times to predict the future. It's a different situation. So I don't know how the sensitivity to initial condition will play out in that case. So, that's a great paper. So we should try.
Thank you.
Yeah. Data-driven things are actually driven with.
Okay. Yeah.
Okay. So I want to ask basically, will AI be able to do well in extreme events?
Well, that's another open question. People, of course, are very much concerned with extreme events. And the issue is usually the fact that the machine learning systems are trained, right? So they're trained on some data sets. So the question is, are they capable to predict something that they've not seen in the training data set? The jury is out on that. There are results that seems to indicate that they actually can, and some results that indicate that something is beyond that reach. So it's open. But certainly there is lots of interest and work on that.
I would just like to add and comment on the question Dr. Subodh asked. There was a paper a few years back in, I guess, in GRL, and they have demonstrated that AI models, if the initial perturbation is too low, I mean, very, very small, the AI models doesn't follow butterfly effect. But if it is considerably large, it does. So that is one of the bottlenecks of AI models. That's what they have concluded.
Question from that side.
First of all, sorry. A very interesting talk you have taken from basics to advanced and past to the future. How the data-driven methods and the numerical simulations, how it is going taking care. So it is very interesting. So first of all, thanks for that. And I have just some basic question just to clarification. So you also have projected there is what is the future way of data-driven techniques? How is going to be a next generation of the data methods? So what kind of a challenge we may face for resolving, or it's going to be a numerical side, it's going to be a numerical computation problems, or else like it's or it's kind of algorithms, or what kind of challenges we may have face in this? Thank you.
It's probably a long list, but if the first two things that come to my mind, the first one is that basically all the AI ML system that exists today have been trained on reanalysis. Question is, have we exhausted the reanalysis? Have we extracted everything we could from reanalysis? So that's one question. And then if that's the case, then how you progress? How you go farther than that? Then, of course, there is the issue of reanalysis itself. Reanalysis was made with dynamical models. So can we make AI ML system directly from observation, skipping the reanalysis? That's another issue. Will that allow us to exploit more better the amount of data that is collected every day? We know that the advanced data simulation system use only like 15 or 20% of the data available daily. So if AI ML can help us to increase the amount of data that we exploit. So these are two things. Of course, there are more fundamental challenges. Why the system works? Can we use them to also use them for understanding processes and diagnostics? Can we impose what we think are constraints? Can we make sure that we don't lose mass, water, tracers? So lots of work.
Thank you so much for the inspiring talk. Actually, my doubt is in the picture that you have showed, in the past scope, there is physics, HPC, everything. But in the future scope, I didn't find like physics. My doubt is like if we are predicting an event, like an extreme event, though if you don't know the exact physical process driving that event, do you think like deep learning technique will be helpful in the accurate prediction or forecasting?
Okay. I don't know if you know this, but in the paper that I showed you, in the pioneering paper that did AML, the list of the authors, none of them is a meteorologist. Now, that's of course people scared because we don't need meteorologists because. But I read that in another way, that the kind of skill that and knowledge that is needed by us is at a higher level. That level is becoming too low. So physics is not the end of physics. We need more physics, but we need to push our way of thinking and working at a higher level. And then you can interact and do something new. In a way, it's like, at some point, a word processor arrived, right? So before that, people had to bring manuscript to a typist. And then suddenly you have to learn to type. And now everybody's typing. So it's the same thing. Machine learning is like typing. So each of us has to learn to type. But then you think higher than that, right? So that's what we need to do.
Thank you.
If there are no more questions, let us thank Professor Antonio for the excellent talk. Thank you.
What was that basement experiment?
Nitrogen moly experiment?
Yeah.
What was the experiment that shows the invariance of the speed of light? Let's see. That basically showed that there is no effect. The issue was how electromagnetic probability in the values. And the hypothesis was that it was not really that. Thank you. Or still of a substance that was called ether. Nobody could see, but the only fact. So that experiment showed there was not. It was the basis of Einstein's special relativity theory.
Well, yeah.
So let us invite the next speaker, Dr. Ronan McAdam. Dr. Ronan is a scientist at the Institute for Earth System Predictions, Climate Variability and Prediction Group of CMCC, working on the prediction of the ocean and extreme events. His scientific interests include physical oceanography, forecasting, and the development of user-relevant applications. He has focused particularly on marine heat waves, defining subsurface indicators, and performing the first global-scale variations of marine seasonal forecast. So let us hear from Ronan. Thank you.
Thank you very much, everyone. It's quite difficult to go after such an elegant and inspiring talk with a lot of history. I'm glad you're all staying in the room. One thing I do have, if not wisdom and experience, is results, which is where it all begins, I think. And in particular, I'd like to focus on a particular phenomena today, that of marine heat waves. In Antonio's talk, we saw how the themes of interest have changed throughout the decades, from weather forecasting to extending that window of predictability to climate modeling. If Antonio, Professor Navarra, can't answer what we're doing in this decade, then I certainly can't either. But one thing we are doing is working on extra validation, let's say, and providing more user-relevant products, continuing to look for what they may be, because we are all in this room, we are producers of reanalysis, models, forecast systems, and we need to provide some sort of societal value to that beyond the research that we're doing, of course. So there is this desire to look for tools, let's say, that we can provide society with. So on that note, I'd like to talk about monitoring and forecasting these extreme events. And this is work done over the past 2 years with many colleagues at the CMCC and across Europe. And now I'm glad to say, also including my colleague Saurav Chatterjee, who is somewhere in the room here. We're collaborating with his institution here in India. So we'll begin with a bit of background just to warm everyone up on what a marine heat wave is. We'll zoom into a particular event in the Mediterranean Sea to give a demonstration of how we can successfully forecast such events on the short term. We'll talk a bit more about how we study the longer term characteristics and trends. And an important theme that's going on in the world of marine heat waves now is extending from measuring the surface to the subsurface, because indeed the ocean is not just the upper meter or so, or centimeter measured by SST. There's a whole lot more. And finally, we will look at some seasonal forecasting efforts to predict these few months in advance. So let's begin with some infamous events. These are all, well, in 2021, considered some of the either the largest or the most longest lasting or the most intense marine heat waves on record. We can see none present in the Indian Ocean, which is not really true because there are many and they have been studied. One that we study in great detail in Europe is the one in the Mediterranean, 2003, still very much a record-breaking event. There is this event in the Northeast Pacific in the mid-2010s, which is otherwise known as the blob. I think there's been a second blob since then too. And you can see various other events either in gyres or upwelling systems and close to the coast and some more open ocean. And here you can see a description, let's say, of the intensity, the duration, and the size as depicted by the size of the circle. So there's some frightening intensities and some frightening sizes, let's say, and some of them are considered more extreme than others. So a great deal of effort has gone into describing them, and because they have a range of impacts. So as we might expect, temperature, when it goes above a certain threshold, as it is for us, causes either great discomfort or even mortality. And in the ocean, that can, of course, have a knock-on effect to either our economic activities for the blue economy or conservation efforts. But it's not as simple as heat bad, heat kills. Okay. This is the example of the blob. There's some papers talking about how there were winners and losers in that marine heat wave event. So some species suffered, and some, perhaps more of the predators, they benefited from these warmer temperatures. In the Mediterranean, we have some stark examples of mass mortality of coral reefs. So these are, of course, species, life forms that are fixed. They cannot escape extreme heat. So as we've seen, for example, in the coral reefs around Australia, there's been massive bleaching events in recent years. Particularly interesting example is to do with lobster farming in the northwest Atlantic, so between America and Canada. So in that year, was it 2012, there was a marine heat wave more in the spring, I think it was. So just before the hatching season, let's say, of the lobsters, or the harvest season. So the harvest came earlier that year, and it was a massive one. But the thing is that the lobsters change position. They move, I think it's down from Canada, or perhaps up from America towards Canada. So instead of, I think it was instead of the Canadians getting the large amount of lobsters that year, the American fishermen got it. And there was a great, bit of the diplomatic struggle there between the fisheries. Some American colleagues have told me some American fishermen went out armed with guns. I don't know how true that is, but you can see how it's that, you know, you can introduce these complex dynamics to even international relations here and local economy. So an interesting range of impacts. But what is a marine heat wave? Well, for a long time, decades, we've been interested in extreme temperatures in the ocean because of the impacts I've just described. But about 10 years ago now, the group came together and said, we need a framework. We need a way to describe what events are actually causing the damage, to kind of separate them from the extreme but less damaging events. So Hodde et al., based on definitions of atmospheric heat waves, said a marine heat wave is an anomalously warm event that lasts for 5 or more days with temperatures warmer than the 90th percentile. Generally, we're talking about anomalous event, okay, but they have come up with a specific way of defining anomalous. For us, anomalous might mean something else. For certain species of fish, extreme means different things, different temperatures. But they, to kind of focus on a historical, well, a universal definition that can be applied across time and space, they went with this statistical-based methodology, which looks something like this. You take a threshold, which since then has nearly always been taken to be the 90th percentile for each location, based on a 30-year historical baseline period. And any exceedance of that threshold for longer than 5 days is considered a marine heat wave. So, of course, there is this arbitrary nature to the definition, which in some places might be more meaningful for species, in other places less so. And that is causing a lot of headaches in the marine heat wave community. People are saying, well, is your threshold a percentile or is it an absolute value? What period are you using for your climatology? Are you detrending because perhaps you want to remove you're assuming a linear warming signal, an anthropogenic warming signal, and you want to just look at the interannual variability? Some people are saying in the Mediterranean, for example, where there's a sharp trend, there's many more marine heat waves simply because we are always above the past 30 years threshold. So people are saying perhaps that's a less useful indicator. And so there's many more open questions. So there is this argument going on. In the meantime, we at the CMCC are trying to be pragmatic and take this universal definition and work with it and assume it represents to some degree the extreme and damaging events in various parts of the ocean. So let's have a look at one of those events, which at the time made the news actually across Europe. So this is page 6 of the French newspaper Le Monde, which has a very nice graphic there showing how the anomalies in the SST at that time were about 5 degrees greater than the climatology. And so we, with some of the regional scale satellite data here, 5 kilometer resolution, we had a look at the area that the marine heat wave was covering and the anomaly above the climatology. And you can see there was large proportion, a majority of the Mediterranean covered at some point during that summer. And if you consider the activity, which is simply a combination of the intensity and the area of the basin covered, we compared 2022 in the black with some previous record-breaking events, let's say, such as 2003. And we found that when you do the sum of the activity over the whole summer, 2022 was considered record-breaking. And then the year after that, we did it for 2023, and that was record-breaking again. And then the year after, we did it for 2024, and guess what? It was record-breaking again. So we're looking forward to this summer to do it again. And again, there's the discourse of we have not taken out the warming signal. So a lot of this heating is perhaps due to the linear trend, well, of the past few decades of climate change, and partially due to interannual variability. But nonetheless, that's one way we are looking at marine heat waves on the Mediterranean basin. We also, at the CMCC, produce a regional scale forecasting system for the Mediterranean. So again, 4 to 5 kilometers resolution, 10-day forecasts. And they did quite a good job of capturing the details of the marine heat waves, so the onset, the decay, and the various breaks in the marine heat waves, which is, I guess, the goal of short-term forecasting. You want to be able to get these details. In the Ligurian Sea here between France and Italy, we see marine heat wave conditions for most of the summer, but there was some respite, which, well, actually, that was one of the areas which was less well forecast, perhaps. But you can see the ups and downs relatively well captured by the forecast in blue, and the orange is showing the marine heat wave occurrence. And the same for another area which is very important for aquaculture, fisheries. Here we have more short-term duration heat waves spread apart, and nonetheless we were able to capture those with the short-term forecasting system. So quite an encouraging result for the short-term forecasting. As we've heard, everyone is playing with machine learning today, and indeed we did that a few years ago, actually published last year. So I remember I think it was November of 2022, my colleague Giulio Bonino came to me and said she was going to prepare this study of machine learning of SST in the Mediterranean. She'd like to include me, so when the draft is ready, she would send it to me. I said, great, and this was November. In January, I get back from the Christmas holidays, which in Italy, you know, we take a good bit of time out, and the paper was already there. I said, how did you do that? And she said, well, come on, it's just machine learning. You take a few predictors from ERA 5, you download the Python modules for CNN, random forest, whatever you want, you put them in, and in a day you have your forecasts. Great, easiest paper ever. Not saying everyone's okay. The PhD students in the room shouldn't be copying and pasting that. We have to be a bit more innovative. But the main point is here, the dynamical system, which I showed you on the previous slide, MEDFS in blue, is sometimes outperformed by these very cheap methods. So here we have the RMSE for various regions in the Mediterranean. And particularly at early lead times, we are adding value in terms of lower skill compared to the dynamical systems here particularly. And when it comes to measuring the skill of marine heat wave prediction, it's very much the same case. So the extremes of SST are captured. At the moment, it's, I guess if you consider the whole 7-day lead time, they're about equivalent, but you know, the skill is there. And all of this from, I think it was 7 predictors taken from ERA 5, I think maybe up to 10 days before. So short-term forecasting with marine heat waves, absolutely possible, and you know that's encouraging when you think about providing tools for aquaculture and conservation efforts and so on. Besides that, we have looked at defining marine heat waves again with a bit more practical use. So far we've just looked at the sea surface temperature. There's a colleague of mine at CMCC who says at the end of the day, the only stakeholders for SST are surfers and mosquitoes. If you're coral reef, or you're any species of fish which is migrating vertically throughout the day, you need to know information below the surface of the ocean. So that's what we attempted to do. And at the same time, we took into account that in the Mediterranean, you have a very interesting kind of economic, geopolitical situation, that there's many countries which have national waters in the Mediterranean. And the national waters are very sub-basin scale, nearly local scale areas, which could demonstrate very large differences between them, even though they are quite close. So we have these exclusive economic zones. And at the same time, as I say, we need surface and subsurface information. What we did at the time, and I'll explain how this isn't perhaps the best approach, but we took a pragmatic approach of using, instead of SST, the ocean heat content for various depth ranges. So here we have, of course, the equation for ocean heat content. And we did that because, as I said earlier, most species which are mobile in the ocean have some sort of daily vertical migration. Okay, this is an example of a tiger shark, I think, in the Mediterranean, in Western Australia, which is probably not very vulnerable itself to high temperatures, but plankton behaves the same way, and all sorts of species in between. And you can see how there is this, in 24 hours, I think, massive cycling between the subsurface, 80 meters, and the surface. So they're foraging, they're resting, and this needs to be taken into account. Because, of course, if the temperature at the surface is extreme, it's quite easy for fish to just escape, go below the mixed layer depth. So we thought we need to define extremes on the whole water column. And now, again, what do you choose? Do you choose 20 meters, 40, 100? It depends what you're studying. Here we chose 3 kind of representative subsurface marine heat wave indicators. These are the trends in the Mediterranean for the SST and the upper 100 meters ocean heat content. And you can say on a basin scale, yes, there is similarity. We have larger trends in the eastern side compared to the western side. But if you consider the overlap here of the exclusive economic zones, you can start noticing some subtle differences, perhaps some shifting of patterns laterally and also vertically. So already there's some evidence that that's a kind of good framework to have for these extreme event indicators. Here's two examples of either an event which was at the surface and wasn't present at all in the subsurface, or one that was, well, present but broken up in the surface, but continuous in the subsurface in terms of extremes. So there is a variety of events out there. And I should point out that now people are looking at marine heat waves through the whole water column, not just taking chunks, which is a very valid approach scientifically. Of course, more computation expensive, etc., but that's not the end of the world. Here, as I say, we're being a bit more pragmatic, let's say, assuming the whole depth is important information. So we also had a look at how these characteristics change with depth. And in general, a lot of literature will say that given that the anomalies below the surface, because they're less impacted by atmospheric variation, they will decay slower. So marine heat waves will be longer, perhaps less intense. And that's generally true. But when you start looking at the local scale, you start getting some interesting exceptions to that rule. For example, the intensity here, about in this area, sort of the Eastern Mediterranean, you start getting greater intensities below the surface. So there is something here going on with the downwelling of warm waters, which we haven't figured out yet, but there is a vertical motion there, which is causing the heat to accumulate, let's say, in this depth range, more so than at the surface. For the duration, yes, there is an increase in duration with depth, but that can change quite quickly, even in the space of sort of 10, 15 degrees latitude, okay? And then you have these small features. So it really is good to have, obviously, a local scale view of what's going on. We also looked at the trends, of course, and anywhere that isn't covered in the black shading is a significant trend. Unsurprisingly, given that in the Mediterranean, the warming is twice the average, twice the global average. Here we have, okay, there's lots of information. I'll just go through it quickly. We have the map for the mean on the left and the trend of the SST marine heat wave characteristics, as we saw before, number, duration. And from that, let's say we do a kind of simple hazard analysis. We want to provide some information to the countries or companies even. And you can frame this in terms of a top 10 list. So a top 10 in terms of the mean duration of marine heat waves. So I think Israeli waters here, first place, followed by Egypt, etc., etc. And our point is quite simply, when you do that for the subsurface, you get a different top 10. So assuming this would be the basis of some sort of hazard analysis, you would need to provide both information for subsurface and surface. Yes, it's more information potentially for a stakeholder, but it's very important nuance, I think. Either way, Egypt here, for example, is first place, second place, but there's some, I think that's, I can't remember what that is, Montenegro maybe, not appearing. It's an example of something that didn't appear in the top 10 of the surface averages, but did in the subsurface. Okay, so we've had a look at the differences between subsurface and surface, and we've tried to argue that the subsurface indicator is more relevant for various stakeholders. Useful product, of course, would be forecasting, particularly seasonal forecasting. And so that's something else we do at the CMCC. This is an example of the product that we might provide to the Copernicus Climate Change Service, SST anomaly taken 2 years ago. But on the Copernicus, there isn't yet an indicator for marine heat waves. So we were trying to push that, trying to show some validation of a forecast system for marine heat waves. And we did that with our CMCC SPS 3.5 system, which of course is a coupling between the various Earth system components. Here we have a reforecast period 93 to 2016, which you might remember, it was recommended a 30-year period for the climatology period. Here, we don't have that luxury, unfortunately, but, as I say, sometimes pragmatic decisions have to be, put forward. We have a 40-member ensemble and 6-month forecast period and a 1/4 degree ocean resolution. So that's what we can do the forecast with. And of course, we have SST, and all the systems that provide for Copernicus provide SST. Unfortunately, for the subsurface, we were quite restricted. So, in fact, publicly available, there's no subsurface data for the ocean. Actually, after this paper was published, they released mixed layer depth, isotherm depth, but nothing for temperature or ocean heat content below the surface. So we just worked with our own seasonal forecast system, and very luckily, the group at CMCC had saved the ocean heat content for the upper 40 meters, and we'd previously shown that that differs quite a lot from the surface characteristics of marine heat waves. So we pushed forward and used that as a measure of subsurface marine heat waves. The problem here is, okay, we have the forecast data. What do we use to validate? At the surface, you have satellite-derived SST. You have many products. You have great choice, let's say. For the subsurface, globally, we used the Global Ocean Ensemble Reanalysis. Again, another Copernicus product, one which the CMCC contributes to. This is the GREP, which, again, for the spatial and temporal domain we're looking at, was the best bet in this case for representing marine heat waves in the subsurface. So what we did for all the products, we took these kind of seasonal indicators of marine heat waves. So the number of marine heat wave days, for example, shown here, the strongest intensity, and the number of events per season. And of course, we were looking at the summer. So in the Northern Hemisphere, we have Northern Hemisphere summer, and Southern Hemisphere, we have different representation, of course. And here are some results. So here is an example from the Northeast Pacific. Again, the blob we were talking about earlier. And we have, on the left, the satellite data, the reanalysis. So this is the benchmark, let's say. And we see already that the subsurface marine heat wave conditions lasted a lot longer than the surface. So perhaps at the surface, they were broken up by short-term winds or weather patterns, but not so much in the subsurface where the heat could remain, and kind of the anomalies would decay a lot slower. The forecast, although there is some underestimation, and I should say these are taken, initialized in May and predicting the forecast of May, June, July, August. They do capture the increase in the subsurface marine heat wave days, but also the patterns quite well. And if you consider the time series, you can see the blob sticking out in the mid-2010s and the increase in skill from the surface to the subsurface. Not much, because the surface is already well predicted for the Northeast Pacific. There's a very large influence on seasonal timescales of ENSOL, and indeed that contributes a lot to the skill. But nonetheless, we're seeing two things here. A, the record is different. As I've mentioned, the number of marine heat wave days are greater for the subsurface, but also there is a slight increase in skill. Okay, a slight increase in skill. Not perhaps a fascinating result, but then we look somewhere else. We look in the Eastern Mediterranean. Here, in 2003, the satellite data showed how this was very much a surface event with some downwelling of heat, let's say, some subduction in this region in the northwest part of the Mediterranean. And the forecast hugely underestimated the number of days. So well, in terms of the geographic pattern, maybe, but not very helpful, that forecast. But on the, if you consider the full historical period, again, you see two things. One, the difference in the record. So here we have the subsurface marine heat waves, perhaps more dominated by this linear trend, this linear warming, but also with some important interannual variability. For the surface, the 2003 event really sticks out. So it gives you a very different record of what was going on in terms of extreme heat, which is the first important point. And the second one is that the correlation goes up from 0.3 to 0.93, which is a considerable increase. As I say, both are important, but we argue that the subsurface has greater value, and here also greater accuracy in the forecast system. despite the ensemble spread, which you can see in the bars here. And we looked at that globally. I think we're coming up to the final slide now. Final few slides. So we have here on the left the skill of the subsurface marine heatwave forecasts, number of marine heatwave days, strongest intensity, number of events. Patterns of skill very similar, and for those of you familiar with seasonal forecasting, you'll see it's very much a pattern of skill dominated by the influence of ENSOL. So you'll see for SST, not just extremes, a similar kind of skill pattern. Number of events is something that's harder to detect on a seasonal timescale because it's very much sensitive to the shorter term variability, which perhaps isn't picked up here. So less wider area of statistical significance. Finally, we have the comparison to the surface skills. So red is showing where the subsurface predictions are more accurate than the surface, and the black is showing the statistical significance. In the tropics, when the tropical Pacific, that's very well predicted by, for SST, so you can't have much of an increase. Actually, tropical oceans, Indian Ocean, to a lesser extent, the Atlantic Ocean, you see an increase in the skill there for the subsurface. And again, it's opening up regions of the mid-latitudes to predictions of marine heat waves, which perhaps, areas where you wouldn't have significant skill for the surface, but you do for the subsurface. And we looked into why, and basically on a general scale, the decay of the ocean heat content anomaly is much slower. So on seasonal timescales, there's more of a persistence, let's say, than there would be for SST. So it makes sense that the skill increases. That being said, we did compare to a persistence model, and it did beat it significantly elsewhere. So it's not just persistence here. Okay, so that's a bit of quite a detailed, let's say, overview of what we've been doing at the CMCC recently. I hope there's some inspiration on how to take that forward and apply it to other areas, and a bit of an indication of how we're studying these extreme events. As I mentioned, I've got the great pleasure of working with Saurav here, and we'll be taking this forward, and we'll be dealing with the problem of defining marine heat waves and how you provide ocean indicators for sustainable development. But the key is no one size fits all. A heat wave for me is very different to a heat wave for you, and that's the same for marine heat waves. And within this project, obviously for CLIM, we'll also be assessing the national observing capabilities, not just for temperature, but for extremes. So what do we need to be able to measure extremes? As you've seen here, I've relied heavily on reanalysis, which for us at the CMCC, we produce it. We like to say it's a ground truth, but of course, there are differences to the observations. And finally, we will be looking at CMIP6 projections, Cordex, MedCordex, and looking to improve the Earth system model representation of these extreme events. I will leave you with these take-home messages, which I've just mentioned, and thank you very much for your attention.
Thank you, Ronan, for the interesting talk on the heat waves. Not only SSTs are important, subsurface parameters, heat content is also important. That is one of the important message what you got from your talk. So now let's open the floor for the questions. Do we have any interesting questions or discussions?
Thank you for an interesting talk. So we are also working towards developing a seasonal framework for forecasting these marine heat waves. So what is your suggestion? Should we remove the trends or should we retain them? Because we have a long hindcast of about 37 years and trends are there. So
we suggest both. Looking at the original data, let's say, the original SST, but also the detrending. You need kind of two definitions in parallel for two reasons. I mean, one, you might want to, in a cheap way, let's say, take out the signal of climate change. So assuming it's a linear trend, let's say over the past few decades, so that you can study more the interannual variability. And that's something I think that's commonly done for seasonal forecast validation, because a lot of the skill in the seasonal forecast system comes from the initial conditions having, of course, that signal of trend. That's one thing we did actually in the paper here, which I didn't present. We took out the trend and then kind of recompared the skill. And of course, your area of skill shrinks, but there is still some capability there of the system to capture the interannual variability of the extremes. So both.
Okay.
More work.
Yeah, thank you.
Welcome.
Hello, thank you.
Plots is showing more number of heat waves in the recent years. Then why do you want to remove the trends then? But in the plots you have showed, plots, there are a lot of heat waves in the recent period.
Yeah.
Like so then what is the point of removing the trend from that?
The point would be, well, as I said, there's 2 points. One is to understand how much of this is due to the signal of climate change. Now, there are proper ways of doing that. There are attribution studies, okay, where you can quantify the impact of climate change on the duration and intensity. But the kind of first step is to see how much of this signal is due to interannual variability. Okay, so it's a way of extracting the interannual variability, let's say, which, as I mentioned, for the seasonal forecast system is an important way of validating, because you're separating the skill from the initial conditions and the actual dynamics, the processes represented in the forecast system. But that's the point.
And in your one plot where you are showing the heat waves over tropical and extratropical, yeah. I find that the number of events are very, very less over the tropical oceans.
Which one?
The first, if you go back and you...
Way back.
Yeah, way back in the first slides.
Yes. Okay. I know what you want to say here. Here.
Yeah. So there is most of the events are confined to extratropical regions rather than these tropical regions. So because of the definitions you have used, or
no, this is not a good representation. If you take this definition, right, exceedance of 90th percentile, technically you have the same number of marine heat waves everywhere. So I see papers where they say, oh, we have found marine heat waves in the subsurface. Wow. Well, of course, because you're talking about extremes relative to a statistical threshold. In that sense, there are extremes everywhere. Here, they've taken some of the more widely studied ones, perhaps some of the more impactful. And some of them are tropical indeed, and some of them less so. Indeed, every time there's an El Nino, there's often a bit of the El Nino period, which is marine heat wave. There are some papers now saying actually that you have El Nino and an extra level of variability caused by other processes, which causes marine heat waves. That's interesting. So it's not just El Nino, but everywhere, essentially.
Thank you.
There's a question back there.
We have Shika.
Yes. Thank you for this interesting talk. What do you think are the main drivers of these marine heat waves? I asked this question because this is a 5-day or a slightly longer event, generally, as per the definition. Mm-hmm. And now when you are studying the subsurface, there has to be some influence of long-term dynamics into it.
Yes.
Right? So, but it's a very short period of time, the event. So what do you think is the main driver for this?
First, I'll comment on the choice of 5 days. That, again, I wasn't there when they wrote this paper. I don't know what I would have chosen, but it was chosen with biological implications in mind. The idea that after 5 days you really get the biological impacts. But of course, that now with lots of driver studies being done, that impacts on what we find. And a lot of people, first of all, found low winds, for example, globally. In general, let's say low winds and less latent heat loss to the atmosphere. Okay, but then the question is, what's causing the low winds? What's causing those changes in latent heat? They are, according to the current literature, mostly, globally speaking, atmospheric based. So the heat is coming from the atmosphere. Unfortunately, most of these studies are done with SST. And even within that, there are interesting differences in the Mediterranean, for example. We have these subtropical ridges which come over from North Africa and bring heat. But further north in Europe, we have blocks, the more persistent features. So there's already a difference in the circulation patterns. And the question now is, what is causing the heat to accumulate. And in my opinion, it's a mix. There's heat, yes, coming from the atmosphere, but then you have the ocean processes which bring it down and maintain it in certain positions. One interesting exception, and surely not the only one, is I think East Australia, the Tasman Sea. I think actually that's present here. Yes, so 2017. Most of the heat there they found was actually caused by a strengthening of the current, which comes down from across the eastern Australia. So a lot of heat transport coming from the tropical Pacific, not so much the atmosphere. So both are possible.
Yeah, thank you. Talking about the 2003 Mediterranean marine heat wave. So just back, you were explaining that atmospheric circulations like stationary Rossby waves can cause these kind of heat waves. But back in 2003, I think this happened in May, and there was a follow-up heat wave in the month of August due to a blocking system. So how do you see the effect of this background marine heat wave on the atmospheric blocking?
Also, I think this of the heat, the ocean heating on the atmosphere.
Yeah, in that case, I guess in 2003 it was the marine heat wave, and then that was followed by the atmospheric blocking in August. So in that case, this happens first, and that comes in later. So
interesting. This happened first, I think, because we've seen for the Mediterranean, you don't get blocking because before the block you have ridges, right? And the ridges are quite sporadic. They come and they go. They don't last so long. But we found that when you get frequent ridges, the ocean manages to retain the heat. Okay, it doesn't dissipate it fast enough. So the next ridge comes along. You don't get the blocking forming above the Mediterranean. The blocking, which persists, happens further north, towards the British Isles, Scandinavia, northern central Europe. And of course, they persist in different kind of heat wave. What comes first? I'm not sure it's the marine heat wave that's then having some sort of knock-on effect on the atmospheric circulation here. Could well. I think it's just the fact that within Europe, you have kind of two domains here, one where the ridges are important, one where the domains. In the Mediterranean region, there is a great concurrence between atmospheric and ocean and marine heat waves. So they happen at the same time for the same regions, generally.
Maybe the surface wind over such a vast ocean, if there is some advection, like southerly intruding the atmospheric pattern, so that can have a positive feedback on that circulation.
As well. The winds in the Mediterranean that we found to affect most to kind of instigate the marine heat waves, we have winds, we have northwesterlies coming over this region, which really cause a lot of variability in the SST. So we often see great intensity there, and also here. So we kind of see marine heat waves, they start here because the wind's coming from the northwest, they switch off, and then eventually, possibly that's where advection plays a role, or the influence of the wind extends a bit here, but the marine heat waves, especially in 2003, they start here and they grow outwards, okay? Or vice versa, they start here and they grow towards the center, because those are the two, let's say, more powerful wind systems.
Thanks.
Yeah, thank you for the talk. Just I have one quick question. So when we're taking a forecasting scenario, so you have considered for the 90th percentile of the data for the last climate of 30 years, world climate. So when it comes to a global scale of skill, but there will what causes the main drivers for the skill in high and low variation? So because the terminology should be, are you thinking like, because like identifying the case should be improved, or like we have to work on that, and what makes this the skill very low and too high? Because same rating it's not applicable everywhere, or what do that? Is that?
So you're saying the difference with latitude?
Yes.
Correct. I mean, as I mentioned earlier, most of the trophics on the seasonal timescale, ENSOL is a big determinant of the skill, and that influence also creeps up towards the northeast eastern part of the Pacific, so where we saw the blob up here. When it comes to the Atlantic, it's a bit difficult because we found in other papers that the seasonal forecast skill for the tropics is relatively low there, and it could be to do with the initialization. There have been experiments done on the data used to initialize the forecast system, so the data used in the assimilation, and some of it has actually taken away skill instead of adding it. So it's a bit of a peculiar area, let's say.
Yeah, that means
representation of the initial conditions as well.
Yeah, that means it's related to the data input and the analysis data what you're using. So it is based on that.
Yeah.
Okay. For the question, actually, when you're using this machine learning, many people have this extreme. So in past, the extremes are different, and future scenario, the extremes are different. We put the same criteria for the future scenario. So most of the leaks we will have the marine heat waves, but still, changing in the climate scenario. So how is going to be tackled from this machine learning methods?
The warming.
Means what I'm asking is the extremes, like extremes. So if you turn the model or something like that in extreme, so we'll not have, so we'll have missed some extremes, right? Yeah. So if you put, suppose if you have instead of reanalysis data, if you see MIP7 or something like in future scenario for large emission, so the same technique if you keep, so it will lead to most of the time marine heat waves based on this criteria.
Yes.
So how is going to tally from in and out?
I think depends on the predictors used in your ML model. But let's say one of your predictors is 2 meter temperature. Okay, that has very similar signal to the SST in terms of the warming. So the ML model will kind of automatically see that. Okay, it might see variations in pressure and Z500 or whatever, but it will see a trend in the temperature, and I think from that it would be able to keep predicting the marine heat waves. Again, what would be interesting to do is when you detrend everything and you only have the interannual variability, is the model able to keep predicting let's say the marine heat waves just due to the interannual variability when it doesn't have the help from like the temperature and the linear trend?
Yeah, some studies something you have able to do that already. Any results like something like that? Do you have something that after the isolating the interannual variability? Just what is the scores? Some study it is already done, or like you're in the process?
Yes. I know for the Mediterranean, there's some studies on comparing the interannual variability and the trend component with more sophisticated methods than just the linear detrending, I must say. Yeah.
Thank you.
Okay.
Excellent.
Thank you.
There are questions. Just one.
Yep.
You are doing the seasonal forecasting
of
the marine heat at CMCC.
Yes.
So you also look into the impacts, how marine ecosystem and coastal regions are affected.
Mic is off.
Yeah.
The impacts, no.
Yes.
We at CMCC, no.
Okay.
Not yet, anyway.
Okay.
But that's something we'd like to get towards.
Okay. So let's thank both the speakers for the time.